Hello, everyone. Our group, myself, Preetish, and Onal and Tanishq, are here to present our final project, a console multiphysics simulation of a 5-speed manual transmission. Our goal was to model the thermal behavior of the gearbox under real operating conditions and evaluate how improved cooling solutions could extend its longevity. Manual transmissions are well regarded for their fuel efficiency and driver oriented control. But there is a well documented problem: excess heat. During the operation, friction between meshing gears generates significant heat over time. This thermal load accelerates internal wear, reduces gear mesh efficiency, and ultimately shortens the life of the gearbox. This is the problem we set out to address. Our solution was to build a high-fidelity COMSOL simulation that couples two physics modules: multi-body dynamics, which models the motion of the gears, and solid heat transfer, which modeled how the motion generates and distributes heat through the gearbox body. Critically, we also designed and tested a theoretical liquid coolant jacket as our primary design intervention, comparing the transmission's thermal performance with and without this cooling system in place. The underlying physics is straightforward. Heat is generated at each gear mesh, the point of contact between two meshing gears, primarily through power loss due to sliding friction. As the gears rotate, kinetic energy is not perfectly transmitted. A fraction of that energy is lost as heat at the contact point, and this heat then conducts outward throughout the gear body into the housing. This is exactly what the diagram on the slide illustrates: heat flux radiating outward from the gear mesh, driven by the velocity and friction at that interface. For the parameters, before the simulation could all run, all the geometry and physics needed to be defined. These are captured in COMSOL's parameter table, which acts as a single source of truth for the entire model. The parameters fall into two categories. First, the gear geometry, the number of teeth and pitch diameters for each of the five gear pairs. You can see here for the first example, the first gear has 14 input teeth and 36 output teeth, giving a high reduction ratio suited to low speed, high torque driving. Second, the physics parameters, which include gear ratios, pressure angle, gear mesh stiffness, input torque, angular velocity, which define the operation condition that we're trying to simulate. The gearbox was imported directly from a Fusion 360 file, where the complete 5-speed gearbox had already been fully modeled. This gave us a highly detailed, realistic representation, and you could see the full parts list in the engineering drawing, covering everything from the input and the counter shifts to the synchronizer rings and gear pairs. Within COMSOL, we use the domain partitions, working 12 separate work planes to isolate each pair as its own domain. This essentially for applying gear pair constraints and friction definitions in the multi-body dynamics module. For the materials, structural steel was applied to all domains. This is consistent with real-world manual gearboxes, which are almost universally steel construction. The thermal properties giving our heat simulation are thermal conductivity of 44.5 watts per meter Kelvin and the specific heat capacity of 475 joules per kilogram Kelvin, and the density of 7,850 kilograms per cubic meter. These values are fed directly into the heat transfer module in COMSOL. Importantly, gear elasticity was also derived from the material's Young's modulus and Poisson's ratio, ensuring that the mechanical deformation under load was physically consistent. The multi-body module governs all motion in our model. Its governing equation relates the material density and the acceleration to internal stress divergence and body forces, essentially Newton's second law in a continuum form. We applied a linear elastic material to all domains. A fixed constraint to the gearbox housing, meaning the housing does not translate or rotate, and prescribed motions to the input and counter shafts to simulate the driving and driven sides of the transmission. This setup was repeated for all five gear pairs. Each gear pair we defined a spur gear constraint in console, specifying the number of teeth, pitch diameter, pressure angle of 20 degrees, with the gear elasticity and friction applied. The countershift was held completely static using fixed joints, which is partially correct. In a manual transmission, the countershift does not translate. The engaged gear was selected using a conditional activation expression where n is equal to 1 activates the first gear, n equals to 2 activates the second gear, and so on. The hinge joints allowed the input and output shafts to rotate freely while the prescribed motion node drove the input shaft at a defined angular velocity. The heat transfer in solids module is the second half of our coupled simulation. Its governing equation states that the rate of change of thermal energy in the solid equals the divergence of the heat flux, governed by Fourier's law, plus any volumetric heat sources. The initial temperature was set to 293 Kelvin, representing a standard ambient temperature starting condition. A continuity boundary was applied at the gear's mesh interfaces, ensuring heat flows smoothly through the boundaries. The heat source for each gear pair was defined as a volumetric heat generation rate, derived directly from the body's dynamics results. The heat transfer expression is the heart of our thermal model. It calculates the volumetric heat generation rate, Q, for each pair. The formula multiplies three quantities: the absolute torque at the gear pair, taken directly from the multibody dynamic solution, by the absolute angular velocity of that gear pair to get the mechanical power. This power is then multiplied by the HV factor, which is set standard gear tribology parameter, representing the fraction of the power that becomes heat due to sliding friction at the mesh. Finally, this is divided by the volume of the gear pair to convert total power loss into volumetric heat source in a watt per cubic meter. This coupling, where the simulation feeds heat directly into the thermal simulation, is what makes the model physically rigorous. This slide represents the core engineering in our project. We simulated two scenarios: the transmission with standard air cooling and the transmission with a theoretical liquid cooler jacket applied. For air cooling, we applied a convective heat flux body solution with heat transfer coefficient of 20 watts per cubic meter per Kelvin, a standard value for natural convection in air. The external pressure was set to 293.15 Kelvin. Sorry, for air cooling, we applied a convective heat flux body condition with a heat transfer coefficient of 20 watts per cubic square meter per Kelvin, a standard value for convection in the air. The external temperature was set to 293.15 Kelvin. The mesh was generated using COMSOL's physics-controlled meshing at a normal element size. This approach automatically calibrates the mesh density between requirements of all active physics, in our case, both multibody dynamics and heat transfer in solids. As you can see, the mesh is particularly dense around the gearbox housing surface and gear interface, where stress gradients and thermal gradients are the steepest. This ensures accuracy where it matters the most. The study runs in two sequential steps. Step 1 is a dynamic time study solved for the multibody dynamics solution, capturing how the gear velocities and torques evolve over the simulation period. Step 2 is a stationary solve of heat transfer physics, which takes stabilized motions from step 1 as a heat source and computes the steady state temperature distribution. This one-way coupling motion feeding into the This one-way coupling motion feeding into the thermal is completely efficient and physically valid for a steady operating condition. The results are a payoff of the entire simulation. On the left, the gearbox without the coupling jacket relying on only air convection The steady state simulation reaches approximately 226 degrees Celsius, or around 500 Kelvin. At this temperature, degradation of the gear mesh lubrication is a serious risk, bearing fatigue accelerates, and structural steel begins to experience elevated thermal stresses. This is not safe for long-term operation condition. On the right, the same gearbox with the liquid coolant jacket applied. The steady state temperature drops drastically to approximately 26 degrees Celsius, essentially ambient plus a small operating delta. This is entirely safe and practical operating temperature that would significantly extend the life of every component in transmission. The conclusion is unambiguous. The coolant jacket reduces the peak operating temperature by approximately 200 degrees Celsius, a reduction of nearly 90%. We want to leave with you three reasons why this is worth investing in. First, it's a high fidelity model. By using COMSOL as multi body dynamics with heat transfer on a Fusion 360 CAD geometry, it's not a simplified analytical estimate. It's a full it's a full 3D physics simulation. The heat distribution predicts it spatially realistic. Secondly, the velocity magnitude results from a multi-body's dynamic step where we are verified against every gear known ratio of transmission. The slopes of the velocity time curves match the theoretical gear ratio relationships exactly. Since the heat sources are derived from both of those velocities, the thermal results inherit that accuracy. Third, thermal simulation. Third is the broad relevance. The method demonstrated here, couple motion and thermal simulation with designed cooling intervention, is directly applicable to rotating any machinery that generates heat with electric vehicle drivetrains, industrial gearboxes, wind turbine generators. Thank you for your time and consideration.